Alrighty, welcome to the Chapter 17 video. This one is going to be all about reflection optics. So, treating light as a particle and looking at how it bounces off of things, especially mirrors, both flat and curved. So you can get similar images to what you'd see in a bathroom mirror, which are what we would call, maybe think of as a normal full-size image, no distortion. But then also we'll look at curved mirrors and how they distort the images and how they change the size and orientation and can even make virtual images. Alright, here's a nice little picture. These are all type of mirrors I'm sure you've seen before. They're curved, kind of curving away from you, so that's called a convex mirror. And in a small space, you can actually see a pretty wide range of stuff because all the light rays are getting, well, if they were coming from your eye, they'd be getting bent outward away. So therefore, everything coming from outward and away gets bent in towards your eye. So that's one of the type of mirrors that we'll look at in glorious detail. First, let's review a tiny bit from the last lecture on light in general. We're treating light as a ray here, and so we're ignoring any interactions with super small things that will cause diffraction or interference, and we're just treating it as traveling in a straight line. And so when light arrives at the surface of a location, a couple of different options. One option is that it will pass through, which is refraction, and that's a topic that we're going to cover in the next chapter. Absorption and scattering are both things that could happen, but they're not really topics that we're going to talk about in this class. Absorption just means the particle of light energy got absorbed by one of the molecules in the substance, and the energy was transferred typically to thermal energy warming the thing up. So like, when the sun hits your arm, you absorb some of that sunlight and you feel, warmth. Scattering is when light hits something and bounces off, and then it just keeps going, and so eventually it's going to reflect or refract into a material. So this chapter is all about reflection. So we're gonna focus in and look on reflection of light. Okay, well, this slide I guess I threw in here just as more review. How do you see something? We've already talked about light in general, but the way that you see something is by a light particle, a photon, going into your eyeball. So if you have a laser beam just shining through normal air without any kind of obscurities in it or dust or anything, you won't be able to see the laser beam at all in the air because all those laser beam particles are traveling one way. And the only way they can get into your eye is if they hit something and then bounce into your eye. And so if you put some mist, some chalk dust or something like that, that gives something for the laser beam to hit, and then the photons hit that and they scatter out, and then you can see it. So if you put little chalk dust like that, you can see it. So the only way that we can see it is if it scatters or bounces off of something. And then shadows. Shadows are going to form with nice crisp edges proportional to the size of the object. Again, if you treat light as a ray, you're ignoring the fact that it might bend around those edges by treating this object as large compared to the wavelength of the light. So with this all in the back of our minds, we're going to move on and now talk about reflection. So there's two types of reflection. The first type is called specular. Specular reflection means that the light is bouncing off of a smooth, flat surface. Okay, so if the surface is smooth and flat, then all the incoming light rays are going to hit, even if they hit in different places, they're all going to hit something that's at the same angle relative to them. So they're all going to be coming in at the same angle, and therefore they're all going to go out at the same angle, and they'll stay kind of as a beam, if you will. They won't get broken up. And so the way that we draw this is you draw your surface as a flat object. It could be horizontal or vertical, doesn't matter, but here's our reflective surface in this picture. Then you draw the normal line. Remember, normal line means perpendicular. So it's a math and physics word, normal, that means perpendicular. Sorry. Oh, I can't spell. Perpendicular. Terrible, terrible. Anyway, the reason that we draw a normal line is because the angles are all measured relative to the normal line instead of relative to the surface. So you have to draw in your normal line. Typically, you'll draw that in as a dashed line. And then you measure the angle in from the incident ray of light over to the normal, and the angle out from the normal over to the ray that's going out. So it's really, really important that you measure these from the normal because that's the convention. Why isn't it the other way? I don't know. I mean, it could have been, but at some point in the past, someone had to pick, are we going to measure relative to the surface, or are we going to measure relative to the normal? And they chose normal. So all the rest of the stuff in these chapters is based on that convention. So it's important that we follow through with that convention. And so you can label the angles theta I for incident and theta R for reflected. You can also label them theta in and theta out, or theta 1 and theta 2. It doesn't really matter as long as you have a picture there and they're labeled with your arrows on your incident ray and an arrow on your reflected ray so we can see the direction it's going. It should be very clear and easy to follow. So the law of reflection is very simple. It's probably something that you already knew or could easily assume. That is, the angle in equals the angle out. So when you bounce off of something, the angle that you come out with relative to normal is equal to the angle that you went in with relative to normal. And this is something you see all the time with things other than light. If you're just playing billiards and you shoot a ball off of the wall of the table, the angle in equals the angle out. And pretty much any time things bounce, the angle in equals the angle out, if you're neglecting things like spin and air resistance and whatnot. But just simple motion of an object bouncing off of something else, the angle in is equal to the angle out. All right. The other type of reflection is called diffuse reflection. And this one is interesting because it's what actually allows you to see objects in every day. So I put big bold on this guy. This diffuse reflection, we don't talk about it a lot in physics class because it's hard to calculate. But the idea of it, the concept of it, is absolutely critical to our functioning in daily life. So diffuse reflection is when you have light hitting an irregular or rough surface. So instead of being smooth like a mirror, the surface is all messed up. And it turns out, actually, if you zoom in on a microscopic level, almost all surfaces are rough like this. And so when the light is coming in, even if all the light beams are coming in parallel, like right here, the surface is at an angle this way, but over here the surface is at an angle in the other direction. So the way that the light beams bounce out is going to be all different. And so the light is going to scatter or spread out and go in pretty much all different directions. And so this is really, really useful because let me go back to the other picture. Here, if you shone a laser beam in right here, the only place where you would see it is if you positioned your eyeball, so to speak. This is supposed to be an eyeball. There's some eyelashes. If you put your eyeball right here, you would see the laser beam. But if you put your eyeball anywhere else, you would have no idea that there was even a light on at all to begin with. You wouldn't see the light. You wouldn't know there was a light. Whereas here, if you shine a laser on this surface, the laser light is going to spread out all over the place, and you're going to be able to see it from pretty much anywhere. And so if you want to like read the page of a book or something like that, the light that's coming in, you need it to spread out into your eyeball. So if I'm looking down at my piece of paper, if I move my head over here or move my head over here, I don't want the words to disappear, right? I don't want them to be only visible from a certain specific point. I want them to be visible from everywhere. So I need the light that's bouncing off of them to go in all directions. And so you might have noticed if you have like a magazine with really glossy pages, you can get some serious glare where you can't really see the stuff. If you're at a certain position and if you move your head, suddenly you can see it. That's because the glossier the pages are, the more specular the reflection is. And then you're going to get, if sunlight is coming in at a certain angle, you're going to get a massive glare at just that angle and not at other angles. Whereas if you have rough pages, like a newspaper, for example, then it's going to be diffuse reflection all the time, and it's much easier to read. Okay, now let's talk about mirrors. We're going to assume that the mirrors are perfectly smooth and perfectly flat. So I know that that's not how it is in real life, but that's going to be our approximation when we talk about plane mirrors, so we don't have to worry about slight diffuse reflection. We'll treat it as all specular reflection, where the angle in equals the angle out. Okay, so a plane mirror, a plane just means it's flat. So think about geometry, a geometric plane like the XY plane, flat surface. When you look and you see the light bouncing off of the mirror, it looks to you, if you didn't know there was a mirror there, it looks to you as if the light is coming from behind the mirror. So this happens a lot of times in supermarkets. If you're standing near an aisle and you look down to the side, like this always happens to me when I'm looking at cheeses or meats in like the deli area. You look down to the side and you're like, oh my god, this cheese goes on forever. And it just seems like it's going on. And then you realize like 10 feet away there's actually a wall with a mirror on it, and it's just reflecting back and you're seeing the same cheese that's in front of you. But if your mind is not aware that there's actually a mirror there, your mind automatically assumes that the light is coming from beyond, because your mind assumes that light travels in a straight line path. So if you see light coming from your side, you're assuming there's something beyond that it's coming from. Another example is a restaurant. Sometimes if you go into restaurants, you'll think, wow, this restaurant is huge, man. They have like so much seating. Just extends forever. And then you realize there's a mirror and the restaurant is only half as big as you thought it was. So both of those have happened to me on numerous occasions. I suspect, hopefully, maybe they've happened to some of you as well. If you see something beyond the end of where the mirror is, obviously that's like the next room over. There's some other business over there operating. It's not the actual room that you're in. And so there's not actually any objects there, but where it looks like the object is called the virtual image. So what you're seeing behind the mirror is called a virtual image. It's virtual because no light particles are actually coming from that location. And it's called the image because it's not the actual object, it's where it looks like it is. So for a plane mirror, we'll do a diagram for it in just the next slide. But the formula that's going to pop out of that is d sub I, which is the distance to the image, is equal to the negative do distance to the object. The negative just means it's behind the mirror. So the image and the object are equidistant, one in front and one in behind the mirror. So a plane mirror, it doesn't change the distance something appears. So if you're 10 feet in front of the mirror and you look into it, your reflection is going to appear 10 feet behind the mirror for a grand total of 20 feet away. The height of an image also stays the same. So height and distance both stay the same. So now let's look at some diagrams or some pictures. So if here's your object and here's your mirror, notice they drew in the dotted line as the normal line. If you draw the light ray coming in and you measure the angle in, then you can get that same angle out to draw this line coming out. And now, if some observer is standing over here looking and they see this ray of light coming at them, it looks to them, they just follow this ray of light backwards. They may not know there's a mirror here. They just keep following it backwards, backwards, backwards. And it looks to them like the object is located somewhere along this line. Now, with only a single ray, you can't actually tell where the object is. You can only tell it's somewhere along this line. If you were here when we had that guest speaker for the math and the graphics stuff, he talked a lot about this as well, where you need multiple rays to trace back and see where image is coming from. So if you start to draw more rays, each one of them, you can have the angle in equal to the angle out. These are not parallel, by the way. They look kind of parallel, but they're actually diverging a little bit. And then you trace them back. They will all end up crossing at the location of where it looks like the light is coming from. I like this one a little bit better. It's easier to see that they're spreading out. So the top of the tree will reflect out, and all these will map back to where the top of the tree image is. The bottom of the tree will map out, reflect off, and then trace backwards to where the bottom of the tree is, and then any point in between. So if you have an extended object, you typically only have to choose the top and bottom points, figure out where they reflect to, or appear to be coming from, and then everything else is continuous in between. So the key here is that the mirror is flat, and the angle in equals the angle out. I want to show you a quick thing for geometry that will help you draw these kind of pictures. If you draw an angle in, and you're wondering, crap, how do I draw this angle out? I want it to be pretty accurate, but I don't have a protractor. So you need the angle in and the angle out to be equal, right? So a much easier way to do that is to think of this as a triangle. If you look at this side, when you reflect this thing out, this side is the same in this top triangle here as it would be in this bottom triangle here. So this angle right here is proportional to this side over here. So if these two side lengths are the same, then these two angles will be the same. So when I'm drawing these, what I actually do is I don't worry about the angle. I measure this distance here, and then I make sure it's the same as this distance here, and then I just connect the dot to this dot. And then it guarantees that these two angles will be the same. And how can I do that without measuring with a ruler? You can use anything. You can use the end of your pencil and like map out that much space and that much space. You can use the lines on your paper. I mean, it's pretty easy to get a set distance, much easier than getting a set angle. So I recommend that to help your drawings be more accurate. Okay, let's do a sample problem. Suppose you want to see yourself in the mirror using the smallest possible mirror. How big should it be and where should you hang it? Does it matter where you stand? Well, I guess I need some more space to work this problem out. So let's just talk about it. Let's talk about it, because I got the picture here already drawn. So this is pretty much the solution. So if your total height here is h, right, then your image is going to be back here on the other side. And whatever light particle, in order to see your feet in the mirror, you need to see the light bounce off. but the light is coming up at an angle, bouncing off the mirror and going into your eyeball, right? So the bottom edge of the mirror should be halfway between your eyeballs and your feet. Likewise, to see the top of your forehead, the light has to go from your forehead down a little bit, bounce back into your eyeballs. So the top edge of the mirror has to be halfway between your eyeballs and your head. Okay? So the top half of the mirror is half of this distance, and the bottom half of the mirror is half of this distance. So you essentially are taking half of your total height. So the answer to this question, without drawing another diagram beside what's given here, is the mirror should be 1/2 of your height. And where should it be oriented? Well, the picture shows you right here. Measure the distance from your eyes to your feet and cut it in half, and then raise the mirror up until the bottom edge is at that spot, and or measure the distance from your eyes to the top of your head, cut that distance in half, and lower the mirror from your head height down to that for the top. And then you should be able to see. Now, what if you get closer, or what if you back up? This is kind of curious. So if here's your head, and here's your body, interestingly enough, if you draw this light ray, I know this is terrible drawing, but this angle in and this angle out are still going to be equal. So even if you move closer, the angle here, it gets bigger, but the angle here gets comparably bigger because these are still similar triangles. Just like I was saying, the distance from here to here is the same as the distance from here to here. So since this distance is the same, then this angle in and this angle out will be the same. And so you can actually move as close to this mirror as you want, or as far away as you want, and you'll still be able to see your entire body when the mirror is this large. So moving farther or closer does not affect how much you can see in a flat mirror. In a curved mirror, it will definitely make a difference. All right, let's look at the second question here. Suppose you have a 2-meter bathroom mirror that starts from the ceiling 3 meters high. If you put a ceiling light 1 meter from the wall, how much of your floor will not be illuminated by the reflected light from the mirror? This is a tough question. Let's do this on a new slide. I need to make a new slide. Okay, so here we go. Back to it. Say you have a 2-meter bathroom mirror that starts from the ceiling, which is 3 meters high. Let's draw a room here. It's 3 meters high. The mirror is 2 meters tall, and it starts at the ceiling. So the mirror goes from here to here. So the mirror is 2 meters. The whole room is 3 meters. If you put a light, ceiling light, 1 meter from the wall, so you put a light 1 meter from the wall, so you put a light right here, how much of the floor will not be illuminated by the reflected light? Well, we need to know how big the floor is to say how much will not be illuminated by the reflected light. Oh no, that's not true. Let's check this out. So look at some light beams that come in. This one is going to come in here and go out way over here. This one's going to come in here and come out here. This one's going to come in here and come out here. Okay, so all of this part of the floor is going to be illuminated because some light rays are going to come in here and bounce out. So you can draw lots of rays in here. Come in here, bounce out here. Come in here, bounce out here. I know my lines are not straight. But the point is, this part right here is going to remain dark. And so let's see if we can figure out how much, it says how much of the floor will not be illuminated. So let's try to figure out this distance x. Okay, so this right here and this right here, these have to be the same angle, because this one right here, the angle in by definition from the normal line, and the angle out, these two angles are equal, and therefore these two angles are equal. Okay, so this triangle right here has a right angle, and it's got to be a similar triangle to this triangle right here. Okay, and so we could figure out what this angle is using arctangent of 1/2, but it's absolutely not necessary because we can look at this ratio. 1/2 is this side to this side. That's just the same as x over whatever this distance is, and this one happens to be 1 meter, since the total was 3 meters and this is 2 meters. So the horizontal distance is 1/2 of the vertical distance in this triangle, and this one has the same angle here and here, and so you can see right away that this is going to be 1/2 of a meter. So without doing any calculations other than just in our head, and using similar triangles here, because the angle in equals the angle out, we can answer a question that might have seemed more complex. Cool. All right. Next up, we're going to look at ray tracing diagrams with curved mirrors. So this is a little bit tricky, and now is the perfect time to take a break. Alrighty, welcome back from your break. We're now going to look at how to do ray tracing diagrams to find images for curved mirrors. So if you have a spherical mirror, there's two types you can have. One is called convex, one is called concave. So we're going to look at concave mirrors first. Concave means that the curved mirror is bending towards the observer. So if you're standing here, the mirror is like this. So I always think of it as like a cave that you could walk into. So the curvature is bending, the top and the bottom are bending towards you. I guess the center is bending away. There's not a really good way to describe it. Looking at a picture is the easiest way to understand it. So see this image, curved this way. The light is focused in front of the mirror at a point called the focal point. So when you have light rays coming in, they don't bounce out. They don't all bounce out the same angle in and angle out as it was on a flat mirror, because it's a curved surface. So it's kind of like that diffuse reflection where if the surface is uneven, the light is going to come off at different angles. But here, it's not uneven in a random way. It's uneven in a very mathematical way, which is it's a part of a spherical surface or a circle. And so if you have these done in just the right way, all of the rays coming in parallel will reflect out through what's called the focal point. And that's the idea, is that the light will then focus. So if you've ever burned an ant with a magnifying glass, then you've actually experienced this firsthand. So there's 3 rules that you can use to help you draw the diagram, which will allow you to find the location of the image. The first one is this: any incoming parallel light, and when I say parallel, I mean parallel to this optical axis. So the optical axis goes through the center of this mirror. So parallel rays coming in come out, they reflect backward out through the focal point. So if you come in parallel, you come back out right through this focal point. Okay? And the focal point is located a distance away from the mirror based on the curvature of the mirror, and that's a property, a physical property of the geometry of the mirror. So when you buy a curved mirror, you know the focal point. It's given to you. It's part of the curvature of the mirror, and I have a slide for that in a second. Okay, so incoming light parallel goes out the focal point. And light is reversible in that if it goes the opposite way, the same things happen. So if you have light coming in through the focal point, it goes out parallel. So if you just turn this ray around the other way, if a light ray is coming in parallel, or sorry, in through the focal point, it will come out parallel. So these 2 rules, really, you only have to remember one of them, and you automatically have the other. It's just the opposite direction. And then the third and final rule is, light coming through the center reflects as if the surface were flat. So locally, right here in the middle, since it's changing from curving away to curving towards, at this point the mirror is momentarily flat. So if there's a light ray coming in right here, it's going to come out as if it were flat. Okay? And so you can draw these 3 special rays, and then you can see where they cross, and that will tell you the location of the image. So let's take a look at some examples. Actually, let me see here. I had said light coming in parallel goes out through the focal point. Let's try to prove that. Okay, so I had this idea. I'm going to prove that light coming in parallel goes out through the focal point, and furthermore, the focal length is given to you as half the radius of curvature. This is what it says in the book. So if you have a big circle or sphere, this is the center of the circle, and they tell you that the location of your focal point, the focal length, is exactly 1/2 of the distance. And so I thought to myself, hey, wouldn't it be cool if I could prove it to you guys that this is actually true? So I started to do this. I started to prove it, and I immediately realized that this is not the case. Because I started drawing these pictures, and I realized I tried to force these lines to go through the focal point, and I realized immediately that this angle is much, much bigger than this angle. So if the angle at this local surface right here, if the angle in and the angle out are equal, it won't go through the focal point. And we know the angle in and the angle out are equal, and so therefore this light ray does not go through the focal point. So the proof failed. Let me see here. So I spent some time trying to figure out what was going on. I looked in the book. I looked online. So let's check this out. I think this is not a waste of your time, I hope, but bear with me for a couple of minutes. So I did the logical thing, and I checked online. Of course, that's what you do when you get stuck, right? And I found a lot of different responses. Some of them were fantastic, but here's one that I found. It says, you don't need to prove that. I never did, at least. All of my teachers never asked for it. It was proven by scientists before, so there's no point in proving it. And so when I read that, it just made me want to cry, because I mean, I know that a lot of times some of this stuff you're like, hey, they discovered it hundreds of years ago. Why do I need to learn it? Why do I need to know why it works, etc., etc.? But I hope that you never fall prey to this idea that since someone else has done it, it's not important for you to understand, because they might have made mistakes, they might have made assumptions. There's just so much more to it, I think, than assuming that someone else has already done it and therefore it's a waste of your time. Which is what I discovered, right? I tried to prove something that was told to me in the book, and then I'm like, hey, wait, this doesn't make sense. And yeah, someone else has figured it out, and yeah, I did figure out the answer. But I don't think that takes away from the learning experience that goes into it. So anyway, what I found out is that this approximation, where these incoming light rays come out to the focal point, is only true if the incoming light rays are very close to the optical axis. So according to this picture, any of the light rays that are like really close are going to bounce out here. But if you have light rays coming in far away, they won't bounce out. And that's exactly what happened in this picture. This green ray here, the angle in and the angle out are pretty close to each other. And so it's a good approximation. If I would have done a ray down here, angle in, angle out, and I would draw this normal line, then these two angles are very, very close. So the closer you are to this optical axis, the more accurate they will come out through the focal point. But this purple one is really far away, and so clearly these angles are very, very different, and it's a poor approximation up there. And so the book even goes so far, much later on, after they tell you this is a fact, they much later say, oh, well, by the way, it's not true. So if you want to read about that, make sure you check page 467 in your book. But the result is that a spherical mirror, if you have light coming in all over the place, only the ones near the center are going to get focused in the focal point. The ones near the edge are going to get focused, but not at the focal point. And so instead of having a nice, sharp, clear image at the focal point, you're going to have a kind of image with the edges blurred, and this is called spherical aberration. So spherical mirrors do not give you perfect images. And so that's actually something important that is taken into consideration when you're trying to make a really nice telescope or something like that. So if you want to have all the light focus at one point, what you actually need is a parabolic mirror. So the first thing I thought to myself is, well, geez, why do we make spherical mirrors? Why don't we just make all parabolic mirrors? So then I started looking that up online, and it comes down to cost. So it's very inexpensive to make spherical mirrors, and apparently it's very expensive to make parabolic mirrors. I'm actually not sure why, but that's what I read online. And so if you have something that requires very precise images, then you want to use and pay for a parabolic mirror. But if you're just doing some general optics and it's not that important if everything is crystal clear, then you can get away with using a spherical mirror, and you just have to accept the fact that there's going to be some spherical aberration or distortion of your image. Okay, let's get back to it. So the other type of mirror is a convex mirror, which means it's kind of bulging out towards you. And so when light comes into this one, since the curvature is away, the light is going to reflect away. And so the focal point that it appears that this light ray is converging from is behind the mirror, or inside the spherical. If you continue this sphere around, it's inside. So let me go back to the other one. This one, the focal point, if you continue this thing all the way around, here would be the center, here would be the focal point halfway. Same thing for this one. Here's the center, not drawn very well, but here's the center, and here's the focal point. Okay, so all these light rays coming in, they bounce off away. They get diverged away. So it's typically called a diverging mirror. The light rays diverge away as if they came from this focal point. So again, there's 3 special rules that we can follow to help us locate the image. Any incoming light parallel reflects as if it came from the focal point. So you come in parallel, you bounce out as if you came from the focal point. Any light coming in aimed at the focal point reflects parallel. So again, that's just the opposite. Number 2 is the opposite of number 1. If you come in aimed at this focal point, you're going to bounce out parallel, just retracing 1 and 2 off of each other. And number 3, if you come in through the center, you reflect as if the surface was flat. This is the same as the other number 3. If you come in right in the middle, you're going to come out with the angle in equal to the angle out. Because here at this local spot, it seems like it's flat. So using the 3 special rays, you can locate the image whether it's a convex or a concave mirror. Okay, and then you're going to get different types of images based on the geometry of it and where it's located. So the possibilities are your image is either going to be real or virtual. So a real image means that when you trace all of your lines all of your lines actually cross at a certain spot, and then there's going to be an image located at that spot. That means that it's physically, the light is actually present, and if you held an index card there and you looked at it, you would see the little image showing up on the screen. A virtual image is when you have to trace the lines back to see where they look like they came from. So there's not actually any light coming from that position, but it appears that there's something there, so it's a virtual image. If you put an index card there, it would not have anything showing up on it because it's like behind a mirror, something like that. Then your image can either be upright or inverted. That's self-explanatory. Upside down, right side up. And let's get to some examples. So sample problem ray diagrams. Draw a diagram for a 5 centimeter object tall, 5 centimeter tall, 20 centimeters in front of a concave mirror with a focal length of 15 centimeters. So concave is going to look like this. Focal length of 15. So let's mark off 5, 10, 15. So there's our focal length. And our object is 20, so there's 20. So here's our object, and it's 5 centimeters tall, so something like that. So mine is not to scale, obviously, but it will give you the right idea. Okay, so this is a concave mirror, so the focal point is here in front of the mirror, inside of it. And our 3 special rays. The first one says, if you come in parallel, you bounce out through the focal point. So this one is going to bounce out through the focal point. The second one says, if you come in through the focal point, you bounce out parallel. So this one says, come in through the focal point, bounce out parallel. Put some arrows on these guys. The other thing is, notice I'm reflecting off of this optical axis. I draw this curved line right here just to help me remember that it's a concave lens, not a convex, or concave mirror, sorry. But you're actually reflecting off of the optical axis, or sorry, not the optical axis, the axis of the mirror itself. So you draw it as a flat surface even though you know it's actually curved. And the reason we can do this is because, again, we're assuming all of these rays are close to the center, so the curvature doesn't matter very much right in the middle. So the third special ray is, if you come into the middle, you go out the middle. And again, to get the angle back out, I'm going to measure this distance, and it looks to be about like right there. So I'm going to come out something like, oh, I didn't draw it all that well. It's going to come out right here. And now these 3 rays, I'm not going to be able to fit it on my screen, unfortunately, but if I trace all 3 of these rays backwards, they should all cross over here somewhere. So let me just draw a little sketch here. So here is my object. I've got this ray, I've got this ray, and I had this ray. So they should all cross somewhere over here, back that way. And so you can see right away, they actually cross, so the image is real, but it's upside down. It's going to be upside down. So it's going to be real, and it's going to be inverted. You should also be able to see that it's going to be taller than the original one and farther away. So the height is proportional to the distance because, again, of similar triangles. So it's going to be farther away, upside down, larger, and real. Cool. All right, let's do another example problem. Draw a diagram for an object located 10 centimeters in front of a convex mirror. So convex mirror, remember, is curved away with a focal length 15 centimeters. So here we go, 5, 10, 15. So there's our focal point. And the object is 10 centimeters away, so let's draw it right here. And typically you just draw your object as like a little arrow like this. And if you put the bottom of the object on your axis, then that you only have to worry about where the top goes, because the bottom is just going to be still on the axis. So this is a convex mirror. The focal point, I've made a mistake. Since it's a convex mirror, the focal point is inside of it, right? This kind of curves around like such and such. So the focal length is actually right here. 10 centimeters, it's inside, so it's not right here. Ignore that. So what were our rules? The light ray coming in parallel bounces out as if it came from the focal point. So it appears, this ray appears to be coming from this focal point. Okay? A light ray that's aimed towards the focal point will bounce back parallel. So let's aim one at the focal point. So that guy's aimed at the focal point. It'll bounce out parallel. And finally, a light ray through the center will bounce out at the same angle it went in. So that angle is the same as that angle. Okay, so I have 3 light rays coming out. 1, 2, 3. Obviously, these 3 light rays are never going to cross. They're diverging away. So with a diverging mirror, the light rays will never cross. You'll always have to trace them back and see where it looks like they came from. So this one here looks like it came from here. This one here looks like it came from here. And this one here looks like it came from here. So you can see all 3 of them appear to be coming from this spot right here. So that right there is the location of your image. Okay, it's upright. So it's right side up. But it is virtual. It's virtual because the light rays do not actually cross. You know, if you put an index card right there behind the mirror, obviously there would be no light hitting it. So the virtual it's also smaller and closer to the mirror. So it's a shrunken down image. If you want a simple example of this, take a spoon and hold it up in front of yourself. And you see your face inside the spoon, smaller and right side up. And you want to make it facing away from you. If you want a simple example of one before this, turn the spoon around the other way. The curvature is the other way. And then you'll see that example as well. All right. So you've learned how to draw the pictures. You've learned about the 3 special rays. And you might be thinking, oh my gosh, I don't want to draw a picture every single time I have to calculate where the image is going to be. Wouldn't it be nice if I had a formula? So indeed, if we keep using this approximation that the incoming rays are close to the optical axis, then we can get a simple formula relating the focal distance to the object distance and the image distance. And the formula is as follows. If you want to see a geometrical derivation of this, we can do that in class. I haven't done it myself, but I'm sure we could work together and figure it out. So 1 over the focal length equals 1 over the distance of the object plus 1 over distance of the image. So whichever of the 3 here is your variable, you plug in the other 2, and then you can solve for the unknown. Also, you can figure out how tall the image is going to be. This one's definitely easy to prove using similar triangles. The farther away it is, the taller it's going to be. And so you just look at the ratio of the distances. That'll give you the ratio of the heights, which is called the magnification. So, you know, if the image is 3 times farther away than the object, then your magnification is times 3. If it's whatever it is, it could be, and the magnification could be less than 1. It could be like 1/2, which means it shrunk. This minus sign is just because if the object is on the other side, then it could be upside down. We saw that in the previous example, or no, we saw it in the first example. Yeah, the object was on the same side and it was upside down, so that way the magnification would be negative because that just means it flipped upside down. So negative magnification means upside down. All right, so that's your formula. You can go back and do these 2 examples if you want using that formula, and you should get some values that are reasonable compared to the calculations that we had here. The last thing is, using this formula, there are sign conventions for when you put in a positive or a negative number for the focal length, the distance of the object, and the distance of the image, based on which side of the mirror it's on. And so I want to go through those. They're very, very important. That formula doesn't really help you unless you know these sign conventions. So, focal length, if it's a converging lens or mirror, the light is converging down to a point, use positive focal length. If it's a diverging lens or mirror, you want to use a negative value. So right now we've only been doing mirrors, but we'll soon learn about lenses, and the formula is the same, and the sign conventions are the same, so it's nice to memorize them together. So focal length is positive if the light is converging. It is negative if the light is diverging. The distance to the object is always positive. That's easy to remember. And then the image distance, here we go. If the light rays actually cross and it forms a real image, then it's going to be positive image distance. If the light rays don't cross and you have to trace it backwards to see where it looks like it came from, that's going to be a negative image distance. So a virtual image is always a negative image distance. A real image is always a positive. So for mirrors, the object will be on the same side as the image for a positive one. And for a virtual image, the object will be in front and the image will be behind. Later on we'll get to lenses. But you know, if you have the light rays So basically, if it's a mirror like this, the light rays are going to bounce off, and they're going to converge. That'll be a real image because they actually cross, and it'll be a positive image distance. If your mirror was located like this, and your light rays are bouncing off, and you have to trace them backwards, you trace them backwards, and you see where it looks like they came from, then that would be behind the mirror, and that would be a virtual image with a negative distance. So focal length, positive if it's converging, negative if it's diverging. Distance of the object, always positive. Distance of the image, positive if it's a real image, negative if it's a virtual image. Okay, recap and then we're done. Simple reflection, the angle in equals the angle out. That's true off of any flat surface. And then for curved surfaces, you need to know where the focal point is. Remember, it's 1/2 the center of the circle. So for a spherical mirror, it's cut out of a circular shape. So if here's your center, and here's your mirror, cut like right there and right there, then the focal point is going to be halfway between the mirror and the center. So if you know the radius of curvature, r, then your focal length is half of that distance. So that's kind of handy. You need to know the 3 special rays that you can draw to find the image graphically, and then you can use the mirror equation, 1 over f equals 1 over do plus 1 over di, to calculate the value, and you need to know your sign conventions for f, do, and di. And for a lot of the problems in the homework, I've actually asked that you solve them twice, once using a ray diagram and once using the equation to calculate and verify that your numbers are matching up with your pictures. And we'll do lots of examples in class. I've got a worksheet, etc., etc. So I mean, a very big part of chapters 17 and 18 is being able to draw these diagrams and calculate values that match up with your pictures. So that's all we've got for chapter 17 on reflection. Next up is going to be chapter 18, refraction, where the light is passing through the objects and bending.